Hello, Professor. We are going to present on convolution neural network. Our group number is 109. I'm Josna Pathapati and my teammates are Monisha Mahendran and Lalitha Padkula. So, these are the contents of a presentation. The contents that I am going to present are neural network, working of hidden layers, types of neural networks, convolutional neural networks, history of CNN, and components of CNN. So, what's a neural network? Let's just start basically the biological neuron. As we know, the brain consists of a densely interconnected set of nerve cells or neurons, which are basic information processing units. An artificial neural network consists of a similar simple processors, also called as neurons, but those are artificial, that are analogous to biological neurons in our brain. The neurons are connected by weighted links passing signals from one neuron to another neuron in an artificial neural network. So, from the diagram or architecture, we can see that there are three different layers in a neural network. So let's start with the input layer. An input layer is where all the inputs are fed in the model through this layer. And the hidden layer. There can be more than one hidden layers which are used for processing the inputs received from the input layers and the output layer. The data after processing is made available at the output layer. The most popular approach to machine learning is neural network. So what's the difference between machine learning and neural network? A neural network arranges algorithms in such a way that it can make reliable decisions on its own, whereas a machine learning model makes decisions based on what it has learned from the data, and sometimes a human assistant is needed at earlier stages. So, why do we use neural network? Neural network can help computers make intelligent decisions with limited human assistance. This is because they can learn and model the relationships between input and output data that are nonlinear and complex. Let's get into some applications of neural network. We use neural networks probably when we have so much of data with us and accuracy matters the most for us. For example, let's say cancer detection. We cannot mess around with accuracy here if you want this to be an actual medical applications. And the other major application is stock market prediction. To make a successful stock prediction in real time, MLP, that is multi-layer perceptron neuron, is used. This MLP compromises multiple layers of nodes. Each of these layers is fully connected to the succeeding nodes. Stocks' past performances, annual returns, and non-profit ratios are considered for building the MLP model. So let's get into the working of a neural network. The neuron computes the weighted sum of the input signals and compares the result with a threshold value, which is theta. If the net input is less than the threshold, the neuron output is -1. But if the net input is greater than or equal to the threshold, the neuron becomes activated and its output attains a value of +1. The neuron uses an activation function to do the processing. This activation function is also called as a sign function. And then the output signal is transmitted through the neuron's outgoing connection. The outgoing connection splits into a number of branches that transmit the same signal. The outgoing branches terminate at the incoming connections of other neurons at the network. So, let's look into these functions here. The prevalent activation functions are the linear function and the hyperbolic tangent, where the limits are from -1 to 1, and the logistic, where the limits are from 0 to 1. And then let's get into the rectified linear unit. This rectified linear unit is just like the hyperbolic tangent function. This rectified unit function is also prevalent, and the name for this unit function is ReLU. ReLU is equal to the combination when it is equal to or greater than 0, and it's negative if the combination is lower than negative, that is 0. So, let's get into the types of neural networks. The types of neural networks are RNN and CNN. What's RNN? So, RNN is a recurrent neural network with that works on the principle of saving the output of a layer and feeding this back to the input in order to predict the output of the layer. So, where is this used? This recurrent neural network is majorly used for speech recognition. Okay, so why is this? There are some disadvantages to the feed-forward neural network. As a solution to that, this recurrent neural network is found. So, what are the solution? This can handle the sequential data very easily, and it considers the current input and also the previously received inputs, and then updates the current input. So, it can memorize previous inputs to its internal memory. These are the major applications of recurrent neural network. And next, let's dig into the convolutional neural network. So, what's a convolutional neural network? Where are they used? These convolutional neural networks are used for facial recognition and image processing. Large number of pictures are fed into the database for training in a neural network. The collected images are further processed for training. Sampling layers in CNN are used for proper evaluations. Models are optimized for accurate recognition results in a CNN. And then let's dig into the convolutional neural networks. So, a convolutional neural network neural network type called convolutional neural network or a CNN, it is also called as ConvNet, is particularly adapted processing input with a grid-like architecture like an image. This convolution is actually derived from a mathematical procedure called convolution that is used in MATLAB. The CNN substitutes this mathematical process for matrix manipulation in at least one of the layers since it is a specific type of linear operation. And then let's get into the history of CNN, that's convolutional neural networks. So, the David Hubel and Torsten Wiesel found a simple and complex cells. These are completely biological. These simple cells and complex cells are then advanced by Kunihiko Fukushima. Fukushima got inspired from the origin of Hubel and Wiesel, and he then advanced the basic concept of biological complex cells and simple cells into your artificial S cell and C cell. This was done in the 1980s. These capture complex patterns, example a dog, using complex cells that gathered the information from other lower level complex cells and simple cells that detect simpler patterns. Let's get into the line by Jan Kun 1990s. These provide the model with an example image as the model to predict the label. So these only depends on the edges and bars. So let us think of a laptop, the vertical edge of a laptop. So these only detects the vertical edge. I mean, when there is only the particular edge and bar, but the advancement of this detects the vertical whether it's on any dimension of the space. So this repeats the process until reaching the optional model settings where the loss is minimized. And from the 1990s, there were other findings. In 2005, the Pascal OSI challenge lowest loss plus highest accuracy performance with the model started with approximately 20,000 images and 20 object layers. Now the ImageNet is very popular. ImageNet large scale visual recognition challenge. Currently, the ImageNet dataset contains 14,197 images in 1,000 different object classes. Let's look at the components of working of CNN. There are four major components of CNN, and those are the convolution layer, ReLU layer, which is rectifier linear unit, the pooling and fully connected layer. These layers are stacked upon each other to do an image processing. So for an image, the input image goes through all these layers to get an output.
Coming to the first part of our components of CNN, this is the convolution layer. So it contains basically three components: input data, a filter, and a future map. So input will have three dimensions: height, width, and depth. It also contains a set of filters, or also called as kernels, the parameters of which are to be learned through the training. One image becomes a stack of filtered images. Basically, this point is what the convolution layer is about. So you see a image of a dog here, and these are the three features which I have described for this particular image. So these features can be like 3 or 4 or 5. It depends on our requirement. And basically, with the help of these features, this image will be converted to a stack of filtered images. So, but the process of conversion from this image to this stack of filtered images will be explained in the next slide. So basically, what is convolution? So convolution is nothing but a kernel or a filter will move across the image, checking if the future is present or not. This process is called as a convolution. Calculating convolution is by sliding this particular kernel over here over the input image. So basically what happens is one image patch of the original image is multiplied by the kernel, and its sum is written to the one future map pixel. You can see it here. The kernel, this is an example kernel, but you can see what is happening over here. This will be getting multiplied by the input image kernel, and the output will be called as a convol future. And the next important thing is stride. As you can see, the kernel is moving across the image. But what the stride means is, stride is the number of pixels shifts over the input matrix. Usually, stride will be 1 or 2, and more than 2, that is a rare case. And coming to the padding, there are 4 different types of padding: zero padding, valid padding, same padding, full padding. but the majority cases we use the zero padding. Zero padding is nothing but, you see the image here, right? Zero padding, what we'll do in the zero padding is we'll add zeros over this side on all the four sides of the image. So what does this do is, while we are taking the kernel, with the help of zero padding, we can get the edges more clearly without any omitting of the images. So that is the basic convolution layer, what is happening. And coming to the next part, ReLU layer, this is the second layer, I mean the second step after the convolution layer. So what happens is, this is called as normalization. Why? Because all the negative values which we are getting after the convolution will be updated to zero. You can see over here. So whatever we are getting after the convolution is this table. And what happens, like, it is showing max pooling, but before that, this is what happening here. The input is nothing but the output of convolution. So like, output of one layer will be an input of the another layer. So this is the output of convolution layer, and you can see all the negative values are removed, I mean they are updated to zero. So this is what ReLU layer is all about. And after ReLU layer, we have pooling. So pooling, it has multiple modes: spatial pooling, subsampling, downsampling. Basically, what everything does is, it reduces the dimensionality of each map but retains important information. And we have three different types, like average, max, and minimum. So what does average pooling does? It smoothens out the image. So if we want the particular parts and edges, basically average pooling is not which we will do. And max pooling is the brighter pixels from the image, and darker pixel from the image is the minimum pooling. That's fine. Coming to the future, this is the pool size. You see it here, right? On the max pooling, from this particular thing, the maximum value will be taken here. That is, from this first thing, the 3 is the maximum number, and that is the max pooling. And coming to the minimum pooling, which is the minimum number minus 4 will be taken out. And average pooling will take a sum of this. I mean, the average of it. And this is an example for better understanding. So these two are input images, which has a white background, this is a black background. And average pooling, as said, it smoothens out the image. So, and max pooling, you see that there is no, the image has, like, it is completely vanished. That is because max pooling takes the brighter pixels from the image. And what happens is, max pooling is not suitable for the white backgrounds. And while minimum pooling, you'll get the good image, because like, the brief, like, summary of it is, for max pooling, a brighter, I mean the darker background is preferred, and for minimum pooling, a lighter background is preferred. This is the takeaway from the pooling part. And after this all the layers can be stacked. What does this mean? Means, this is the image, and it is passing through the convolution layer, and then there is the ReLU layer. What we can do is, we can further add in another convolution layer and a ReLU layer, and then we can do the pooling. And again, two layers, we can stack it up, and then we can make it another pooling layer. So what happens with all different types of layers is, the dimensionality will be reduced. That is the main thing. And more this particular complete part is called future extraction. And afterwards, the values we are getting will be distributed as the what we say, the fully connected layer. This is the classification, where the major part of classification will be done. So coming to the fully connected layer, what happens is, these are the values which we have got from the previous convolution, ReLU layer, and the max pooling. So from these four values, like, you can see that we have placed them each here. What happens here is, every value gets a vote. What does that mean? So based on the how much the value it is, every value will be getting a vote. So you see, this is an example. So everything is pointed here. And similarly, there will be everything will be, I mean, everything for the curve. This also get this will also have mapping. And then based on the value, then it is decided. So the thickness of these lines represents weights. You can see it here. For value 1, the thickness of this line is very dark. And coming to a 0. And for this 0, the line is very light, because it depends on the weight. So the thickness of the line, it specifies the weight of the line. And these can also be stacked if we want. Uh, Generally, two fully connected layers will be stacked, but it is optional. That is completely your choice. And from the next part, it will be on weights, bias, and error. My friend Monisha will take over. Thank you.
Talking about weights, bias, and error. Weights are the real values that are attached with each input or feature, and they convey the importance of that corresponding feature in predicting the final output. Weights regulate the signal between two neurons or the potency of the connection. In other words, a weight establishes the degree to which an input will affect an output. Biases are an additional input into the following layer that are constant and always have a value of 1. Although bias units don't have any incoming connections to the prior layer, they do have outgoing connections to their own weights. The bias unit ensures that the neuron will still be activated even if all the inputs are 0. Now, coming to backpropagation. Backpropagation is a process involved in training a neural network. It involves taking the error rate of a forward propagation and feeding this loss backward through the neural network layers to fine tune the weights. An input vector is put into the input nodes, which arrive through the pre-connected path. Input is modeled using real weights. The weights are usually randomly selected. We calculate the output for every neuron from the input layer to the hidden layers to the output layer. We calculate the error in the output. The error is computed as a sum of squares difference between the network output and the targets. The error is fed backward to the hidden layer to adjust the weights such that the error is decreased. We keep repeating this process until the desired output is achieved. A forward phase. By moving from layer 0 to the input layer and to the layer M and to the output layer for each input output pair and storing the results for each node in a layer. Feed forward. In feed forward, the input X is fed into the network. The primitive functions at the nodes and their derivatives are evaluated at each node. In backward phase, we evaluate the error term for the last layer delta and backpropagate the error terms for the hidden layers, proceeding backwards from the final hidden layer. Determining the partial derivatives for each individual error with respect to the weights. Coming to the limitations, they fail to encode. The limitations of CNN is that they fail to encode the position and the orientation of objects. They have a hard time classifying the images with different positions. A lot of training data is needed for the CNN to be effective. CNN tends to be much slower because of the operations like maxpol. In case of convolutional neural networks, is made up of multiple layers. Therefore, the training process could take particularly long time if the computer does not have a good GPU. Applications of CNN can be at various places. Firstly, in face detection. For detection of faces, CNN has showed improved accuracy over previous algorithms, identifying faces 97% of the time. CNN can be used to help reduce the amount of distortion in face. Coming to facial emotion recognition, along with distinguishing between the facial expressions such as anger, sadness, happiness, CNN can also be adapted to perform well with various lighting conditions, angles, or faces within images. It also helps in object detection, where we can detect a wide range of objects from everyday to day items such as food, celebrities, or animals to more unusual ones, including dollar bills. CNNs have been used to localize and identify objects within images as well as creating different views of those objects, such as we use in drones or self driving cars. It's also been used for auto translation in the context of deep learning for automated translation between language pairs such as English, French, Chinese, etc. It's also used for handwritten character recognition, X-ray image analysis, cancer detection, where CNNs have been used to detect cancer in medical images such as mammograms, CT grams. They're able to produce highly accurate results, and CNNs have been able to identify cancerous cells with an accuracy of 95% compared to that of 85 to 90% rate of the pathologists were capable of identifying. They're also used in biometric authentication and 3D medical image segmentation. Coming to the future and scope. Coming to the future and scope, So CNNs can be used in development of large-scale balanced data sets for AI-assisted structural health monitoring. They can be used for video data for multi-class program problems. They have a future and scope in cutting-edge handling and visualization tools for big data, improvements in AI application for both laboratory and field measurements, multidisciplinary research collaborations, and development in data preparation tools. And finally, coming to the last slide, these are the references from which we have done a detailed study, and our presentation was based on all these references. And finally, we would like to thank Professor Rachel Hagemann Blair for giving us this opportunity to present this topic of convolutional neural networks. It has been a pleasure, and we're honored for attending your classes, and we have learned a lot from you. Thank you so much, Professor.